Hi everyone, I'm Chris and welcome back to the lecture on neural networks of this machine learning course. This section is about building neural networks. So, let's start building complex neural networks starting from a single unit, the neuron. A single neuron is the simplest form of a neural network. A neuron takes capital K input variables, x1, x2 up to x capital K. The neuron gives back a result y tilde, the model's output. To calculate this output, at first the neuron performs a linear combination of the input variables x with parameters w. Thereby, each input variable is multiplied by an individual factor w. So, x1 is multiplied with a factor w1, x2 is multiplied with a factor w2, and so on. X capital K is multiplied with a factor w capital K. The resulting terms are summed up, and a y-intercept parameter w0 is added. The result of this summation, denoted by z, is w0 plus w1 times x1 plus and so on plus w capital K times x capital K. The linear combination of the input variables is sketched by the gray arrows on the left side. And the result z is symbolized in the left half of the neuron's blue circle. On the right half of the circle is sigma, which symbolizes an activation function. This is a nonlinear modification of the summation result z. Different functions can be used as activation. For example, a popular one is a sigmoid function. It is sketched on the right side. Its functional relation, sigma, is equal to 1 over 1 plus exponential function of minus z. So it takes z as an argument and gives back a non-linearly modified result. Note that sigma denotes an arbitrary activation function, not only the sigmoid function. However, the sigmoid function can be this activation function. The sigmoid function was used for logistic regression to perform classification tasks. Thereby, the sigmoid function takes a linear model as input. This is our summation z, which contains the linear combination of the input variables. The neuron's output y tilde is the result of the summation after the modification from the activation function. The model parameters w can be determined by fitting the model to data, similar to the models in the previous lectures. We will take a look on this training process later. For the sigmoid function as an activation function, a single neuron and the logistic regression model are equivalent. Consequently, a single neuron with sigmoid activation can be used for classification tasks to distinguish between two classes. To perform a logistic regression with a single neuron is not very exciting. So next, we build more complex structures with neurons to build more complex models. First, we put some neurons in parallel. This gives the so-called single-layer perceptron. Similar to the single neuron, the single-layer perceptron takes capital K input variables, x1 up to x capital K. Instead of being the input for a single neuron, the variables are the input for capital L different neurons. Linear combinations of the variables are performed. For the Lth neuron, For example, the second neuron. Each variable xk is multiplied by an individual model parameter wkl. The weighting parameters for the variables are subscripted with a first index to indicate the input variable they are multiplied with. A second index indicates the neuron for which the parameters are used in the linear combination. Each gray arrow from an input variable to a neuron represents a multiplicative parameter w. Such parameters are also called weights. The summation over all variables together with the y-intercept term w0l gives the neuron's summation zl. The y-intercept term is individual for each neuron, so it is subscripted by L. But it has no connecting input variable, so we set the first index 0. The y-intercept parameters are also called biases. Each sum, the L, is modified by a nonlinear activation function, for example, the sigmoid function. So the summation at the lth neuron, the L, is substituted into the activation function. The capital L results of the activation functions are the model's outputs y tilde L. In our sketch, in the blue circles, the activation function symbol sigma of the lth neuron is replaced by the output y tilde L. This is because we use the same activation function for each neuron, and the output of the else activation function is identical to the output of the else neuron. So for all neurons, we have capital L output variables, y tilde 1 up to y tilde capital L. The parallel formation of neurons is called a neuron layer. The layer has individual parameters for the linear combinations of the input variables as well as the capital L bias parameters. Note that, in theory, each neuron can have a different activation function, but it is common practice to use the same activation function within a layer of neurons. The single layer perceptron shown here uses a sigmoid activation function. So the neural network performs capital L logistic regressions in parallel and give back capital L results for the output variables. Of course, this seems not very spectacular. So this was the reason why neural networks were not of so much interest until someone had the following idea. We can not only put multiple neurons parallel to each other to form neuron layers, but we can also stack layers together. So layers of neurons can be stacked behind each other to form deep neural networks. Such a neural network structure is called a multi-layer perceptron, or MLP. In our example on the left side, the model input X is processed in the left-handed neuron layer by its parameters and activation functions. This layer is called a hidden layer because it doesn't give back the model results. Instead, the output of a hidden layer is used as input for the next layer. The next layer takes the output of the preceding layer and performs linear combinations with the parameters specific for this layer. This layer, in our example, gives back the results of our model. Consequently, it is called output layer. The layers of the neural network are denoted by Roman numerals. All parameters, summations and outputs of a specific layer are superscripted by this layer number. The closer the layer is to the input variables, the higher the corresponding layer number is. So, for example, the hidden layer is layer number 2. The output layer is layer number 1. Of course, we are not limited to 2 layers. We can add further layers to construct deeper neural networks. We will come back to very deep neural networks later in this lecture. Note that the number of neurons is individual for each layer. Now, we will take a closer look on the parameters of this neural network. These parameters are called weights and biases. The weights are the multiplicative scaling factors of an input. The example on the right shows 2 connected neurons somewhere within the neural network. The cased neuron of layer number 2 output values of the variable yk with the layer superscript 2. This output is used as input of the else neuron in the next layer, here denoted by the layer superscript 1. The output of the second layer is multiplied by a weight parameter wkl with the superscript 1, indicate that it belongs to the layer number 1. The summation variable of this neuron is dl with superscript 1. There can be a lot of contributions to this summation. But the contribution from the kth neuron of layer 2 is the connecting weight parameter wkl times the neuron's output yk of layer 2. So the weight parameter w is subscripted by the connecting neurons k and l and is superscripted by the layer it belongs to. Besides the weight parameters, we have another type of trainable parameters, the biases. They represent the y-intercepts in the summation. Each neuron has an individual bias parameter. For the else neuron of layer number 1, this is W0L with a superscript 1. The bias term doesn't connect 2 neurons. It is just an added parameter to the linear combination of the inputs in the summation. This can be symbolized by an incoming arrow from a constant input value 1. So the multiplication with it has no further effect. So in addition to the other terms in the summation variable dl, we have 1 times w0l, which is equal to w0l. Note that the bias term is omitted in most visualizations in the course. The inputs for our neuron layer number 1 are outputs from a previous neuron layer, layer number 2. These are capital K variables y superscript 2. In neuron layer 1, we have capital L neurons. The first of these neurons performs a linear combination of the capital K inputs and adds a bias. This gives V1, the summation at the first neuron of layer 1, is equal to W11, the weight connecting the neurons on the top, times Y1, the first output of the preceding layer, plus W21, the weight connecting the second input to our first neuron, times Y2, the second output of the preceding layer, plus, and so on, plus WK1, the weight connecting the last input to our first neuron, times YK, the last output of the preceding layer, plus W01, the bias term of the first neuron. Similarly, the summation of the other neurons in layer 1 can be expressed. In short notation, we can write the summation at the first neuron. The sum over all inputs to this layer number 1 by k of the neuron layer's weight wk1 times the output of the preceding layer yk, and this plus the bias term w01. Replacing the index 1 by L gives the summation for an arbitrary else neuron of layer number 1. In this lecture, we consider so-called feed-forward networks. These are neural networks where the gray arrows are directed from the input into the output direction. Our examples so far are such feed-forward networks. However, it is also conceivable that the output of a layer is used as an additional input to a previous layer. This means an arrow is directed from a neuron closer to the output towards a neuron closer to the input. But such structures are not considered in this lecture here. Further, we consider so-called fully connected neural networks. These are neural networks where every possible connecting arrow between two successive layers, or the input variables and the next layer, is present. So-called shortcut connections, where the connecting arrow skips at least one neuron layer, are not considered here. Section finished. If you like this video, please click the like button and consider to subscribe this channel. If you have any comments or questions, please leave a comment down below. And thanks again for listening. See you in the next section.